Hello, everyone. I'm happy that you could join us on August. Well, a lot of people are on vacation. So if you're on vacation, I hope you will enjoy this session. So on 1st of August, 3DOptix has released amazing new features. And we would like to use this opportunity to share with you what are those features and how you can use those features. I'm sure you would appreciate that. In this session, we have a short agenda. So let me share with you the agenda for the session. I'm going to talk a little bit about Optics Catalog, and then I'm going to segue to Roman, who's going to talk about diffraction. And then I'm going to take back and talk about custom optics, CAD2 optics, coordinate system, and the power meter. And then I'll segue back to Roman, who is going to finish with polarization, 3D polarization, and user-defined coding. Bear with us in the end because we have a very nice surprise in form of 50% discount for the next week. So I'll give you a coupon code, and I'm going to send you that coupon code over email as well. So without further ado, let me start. So if you open the software, and one of the main feature is our big off-the-shelf optical catalog, which is available by right-clicking on your mouse. Open the catalog. We changed that completely. And this is the new optics catalog. Let me show you how it works. The first major improvement is the search bar. Right now, this is a very enhanced search bar. So for example, if you start by filtering do lens, and then let's pick subtype, plano convex, and then you want to add a filter from the search, for example, 200 millimeter, you would see the autocomplete is here. You press that, and then it adds another filter, and then you get 200 millimeter in each and every name of those products. Now, you can see the filters up there, and as opposed to the previous portal, right now the ability to add optical element is by selecting. So you can select that. You can see here it's smart. You can do multiple selection, and if you want to add them, you see here the blue button at the lower side of the portal. You select that, and you will see that those two elements here appears on the canvas on the same location where the mouse was when you launched the portal. So these are the two elements. Let's go back to the portal. For each and every element, there is an arrow here. You can press the arrow and you can see more metadata about that specific element with a link. You can jump directly to that specific product page. Specifically, this is Edmond Optics. You can select it as a favorite or multi-select, and then you have here on the favorite, you can select that and you see all the elements that are favorite are here. So you can do that as well. And let's deselect those. You can select up to 3 elements, and then you can compare them. You can see here, this is a button of compare selected. You can see comparing the metadata over here as well. And we changed the way that you scroll. In the previous one, you can scroll down and it will automatically launch the next page. Right now, we have here result per page. You can change that. You can up to 100, and then you can move between the pages of your results. So this is already here, and this is available for you, and you can use it. I'm segueing to Roman. Roman?
Thank you, Gil. Hello, my name is Roman Vander. I'm product manager of 3DOptix, and we will start talking with the most exciting feature released on August 1st, diffraction. So the diffraction model we released is the Huygens diffraction, and let me share my screen with you. Okay, So as you probably know, Huygens model describes the diffraction as a phenomena that every point on the wavefront or on the illuminated obstacle starts to behave as a point source. So what we actually do, contrary to what we normally do, because we are non-sequential ray tracing software, what we do here, for every point on the surface number n, we calculate Huygens integrals from every point of the previous n-1 surface. So it's a lot of integrals, a lot of computations. And here, the fact that we are using GPU is very beneficial. So we can compute it quite quickly. And Huygens diffraction uses no approximation. So it's the accurate model. And later we'll describe also the next step and what we do, how we would like to accelerate, and the other models that we will release in the mid-September. So I would like to show you a few examples. What we do here, we actually would like to, simple examples of diffraction. The pinholes, double pinholes is actually a young experiment, a center of obscuration. So in order to do it, you need to upload the aperture, actually your mask. So this feature, what you actually do, you right click on your scene here, for example, and you go to add user defined object. You'll see that this feature, Gil will show you later, it's actually, you can create every element, but also a mask. You go to the aperture here, and you go to the images, and you upload your image from your library using your browser. In the mid-September, we will add a few examples of masks you can use, like pinhole, pin dots, slits, Lena, and you can use them, or you can create your own images. Here, for example, just a second. Yeah. So for example, I would like to upload Lena, the famous Lena, and here I need to show. So okay. Import, and here will be the size of the actual mask on your scene, and you see the image. It will be uploaded in a few seconds, and then you can position it. Just for example, in here you can see it. Just for example, how you upload your apertures. Now I'll remove it. Okay, and back to our scene. Now this scene is pinhole diffraction. If I turn the lights off, you can see very small pinhole here. It's 0.125 microns radius of pinhole. I illuminate it with the plane wave, and then I put a detector at the distance of 100 millimeters. You can see it here, and this is a diffraction pattern. I just run it previously. It takes about 1 minute to run it because of high resolution. You can see it here. By the way, showing again, you see it's a premium feature. You go here in the analysis to advanced diffraction, spot coherent irradiance in this case, or you can go to coherent phase. So this is the image. You can, see every disk, and you see its cross section. So this is what it is expected. Now let's go further. Let's use also, you can see another aperture I uploaded. You can see it's double pinhole. So the same detector, same distance. And if we run the diffraction, you'll see actually the fringes, because two diffraction patterns, each from other pinhole, are interfering here. And this is the cross section. The last one here is the central obscuration. So you see here it's a big aperture. It's actually a pin dot, and we illuminate it. And this one it's very close, because you can see the distance. This is the pin dot, and this is just 0.5 millimeter apart of it, so it's near field, and most of the people would not expect bright spot in the middle, but this is what is called boson spot, and you can see what this look like, and there is a bright spot, or if we do a cross section, this is the famous profile. And the last one here for the diffraction, again the same lens. What we did here, we illuminated with some spatially filtered illumination, so we illuminate Lena. Now what I would like to mention, that if you want to build your image in your spatial filtering system, 4F system, using lenses, at this stage, what you do, you create a phase mask. You remember how we loaded a few moments ago, we loaded the aperture. What you do here, you go again, but now you upload it as a phase image. So you create your own mask, and in the mid-September, you will have few samples. We will upload 1 millimeter and 10 millimeters effective focal length lenses emulated by phase masks. So you see here actually 4F system. So we see Lena at the front focal plane of the first lens, and then the sum of the effective focal length. The lenses are 1 millimeter effective focal length, so the distance here is 2 millimeter, and 1 millimeter of the back focal plane of the second lens is the detector. So if we run it, we see image of Lena. It is inverted because it's double diffraction or the imaging. So this is it, and it ran a couple of minutes. If we want to do something with the Gaussian light source, so it's another feature we just launched on the August 1st. So we can see that when you add a light source, now we have a source type Gaussian, not only plane wave and point source we had so far, we have a Gaussian. So you add a Gaussian, and then you need to specify its properties. And actually, it's a very cool feature because you can use it as a calculator. So here it's 10 micron waves, and you see waves position and the Rayleigh range, divergent angle, and you. But if you change it to 1 millimeter, you see it's recalculated. So actually, you can use it as a calculator before you even launch it, and then you can use it. So what I did here, I created 10 microns a Gaussian beam, and I put rectangular detector 100 millimeters from it. The wavelength is 550. So I wanted to compare it to Zemax, and it's the same. You see 100 millimeters distance. You see it is 10 microns beam, and you see the result. This is the result. This is its profile. You see it's, let's see here, it's 175 waist radius. So this is Zemax. Let's use it as a reference. And now let us see what we got. So this is our spot, and this is our profile. And you would believe that it's the same, exactly the same one. You see 175 waist radius of the Gaussian. Now, a few words regarding the limitations, what we have here, and how we overcome them, and what will be released, and what is actually our roadmap for the diffraction. So currently, due to the resolution and due to the time, we just released this as a proof of concept or proof of design, and it is limited to 0.5 millimeter size apertures, and it is limited to planar surfaces. That's why we are using phase masks and not the lenses. On mid-September, we'll be releasing faster version, and what is more important, you can put real lenses, so the curved surfaces will be supported. You still can use phase mask, but the lenses will be supported. And we do in parallel 2 additional processes. First of all, we would like to add Fresnel diffraction. Fresnel diffraction is much less accurate than Huygens, of course, but it's fast. It is limited to paraxial, and all the limitations, but it's fast because it's based on Fourier transform. So we will be releasing FreeNL1, so you can play very fast to adjust your system, and then when you know that it's okay, you can run Huygens and get very accurate response. In parallel, we're going to accelerate the Huygens one. So we already know how to do it by 100 times, and our goal by the end of 2023 to have 3 orders of magnitude, or 1,000 times faster than it is now. So in this case, you can run actually everything in normal time. So thank you for listening. Now we move to Gil, and I'll be back after Gil with a new polarization feature. So please stay with us.
Okay, thank you, Roman. Can I ask, other than Vika, does anyone have problem with slow connectivity? Because I see that she asked us to show to slow down because her screen has problem to refresh. So if you do have problem, just write it in the Q&A, and I'll try to be more slower. Okay. So right now, I'm going to show you how to create, to generate custom optics. So we have a feature where you right-click when you have the cursor on the 3D layout view. So you do add user-defined objects. And this is the new screen that pops up. The default is spherical, plano, convex, but you can choose between the supported different optical elements. You can change the different parameters here. For example, it's a 25mm diameter, thickness. And what happens is, even if automatically you change the radius, let's assume like minus 100, you see that automatically it changes the subtype here. Or if you go and do, for example, 50 here, again, it will change to concave because of the geometrical properties that we have changed. But let's take it back. And then let's start from let's start from scratch. So spherical lens, and then you can change, as I mentioned, the geometrical properties, or even you can go and deep dive to the surfaces. So let's pick up the front surface. So you can, now it's uncoded. You can do it coded and select between the different options. You can see in the coding chart what it's all about, or you can enable, for example, shape model for scattering, and I'll show you how it works. So let's disable that for a second and just change the lens. Let's do save. And then take what I've created, run the simulation, and you'll see that it is behaving as expected. Okay, move it here, over here. And then what I want to show you is that I would like to change right now let's add the scattering option, and then add here reflectance 100, and then again save. And then what you'll see scattering. Now it's hard to see the rays. So what we've added here under the view option, you can see change ray colors palette. And right now this is spectral ray colors. We'll change it to intensity. And then you can see all the intensity. There are more options here. Directional ray colors or user-defined. User-defined, you can do by source and have them defined from this location, from the appearance. So let's get it back to spectral rays. Okay, and then turn the light off. So this is a user-defined. Again, you can apply optical properties such as coating, as I showed you before. Okay, so now I'm moving to upload CAD to optics. So the way to do that is you right-click on the 3D layout view, you do import CAD, there are a few options to import CAD right now. So the first one is to do optomechanics or optics. If it's optics, so you can go to any product page of an optics, download the step file. This is the format that we support. Upload that. I'll show you that how we do that. So let's pick up one of those that I've already prepared. So let's pick this prism. So I would pick up the resolution, the triangulation. So I would get optics to the highest triangulation resolution. So it will be much more accurate. And I have the option either to use the color that is coming from the step file or the user from 3DOptix. The main difference is if it's from CAD, so typically an optics would become very gray. And with 3DOptix, the colors are much nicer. So I would select that and I do import. I get this notification. And then it will take up to 20 seconds, 30 seconds for that part to be uploaded, converted, triangulated, and then being thrown back to the 3DOptix layout view. And you can see how the progress bar and the percentage are being presented here. And then so I close this. Then you can see here, this is the element that we have uploaded. So let's select this. Let's move it a little bit, change the orientation. And then I can put the element here. And then I can just show you that it has now optical properties. The first one is material. Let's change that to NBK7. So NBK7, I would save that. And then let's move all those parts here that I prepared and then propagate the simulation. Okay, so let's again change it to spectral color. And then I would select the element and I would like to make it transparent, high surfaces, so we can see what's going on internally. And then I would rotate it a little bit. I moved it, but let's rotate it a little bit so you can see that it works properly. So I'm just rotating the element. Let's propagate again, and then you can see that it behaves exactly like a prism with NBK7 material. Now, in this case, you can apply all the faces option that I've showed you when I generated a custom optic. So the way to do that is to hover above the optical element, right click, and then you see more options here, CAD settings, and then choose face to change its properties. So now you see the faces. When you hover about each and every face, it's being highlighted. And then you select one of the faces, and then it opens that specific properties for that specific face. So again, I can do coding, apply coating, and find the different coding here. You can see here the graph that opens, what is the specific coding that I would like to show here. So the graph is changing. Or as I showed you in the customized optics, let's do scattering, and I'll show you that it is working. And now I would run the simulation. And then we would see scattering. I want to see that nicely. Then I will change it to that view. Okay. So now let's bring this back, turn off the light. So this is CAD to optics. This is a very nice feature that you can use if you don't have the optical element in our native library, the off-the-shelf that we already got into the product. So you can always download the CAD file, upload it, and apply the relevant optical properties. By the way, including upload custom coding file. So that's also available. What I want to show you right now is to import CAD, but now as optomechanics. So I've already prepared LMR1. This is the known Thorlabs lens mount. So I'll open this one, select it, and then import that one. Again, this is a very small mount, so it will probably take about 20 to 30 seconds, and then you would see that it automatically pops to the canvas. Okay. So it's here. Let me just annotate it. 100 degree, 180. And now I would put that, let's run here a simulation, because I would like to show you how you implement the same way of face optical properties to mechanical components as well. So let's change the height to 110. And right now I'm going to follow the same procedure as I did to the optics. I'm hovering above the mechanical element. I'm right-clicking, going to cut settings, and then choose face to change its properties. Then when I'm hovering, I can see all the faces. So I'm selecting the right one. Again, let's enable scattering. It is already on 100% reflectance. I close this window. I would run again, and then I would see scattered rays on the surface of this mechanical element. So this is a very, again, nice feature and capabilities that we've added that I'm sure you're going to use and enjoy working with that. Okay, let's turn off the light. So this is in terms of CAD to optics. I want to show you two more things before I segue back to Roman. One is the power meter. So power meter is the ability to show what is the power in a detector. So right now I propagate the simulation. I have here a source, and I have selected, if you can see, this is a beam splitter. Let me show you what it is. It is from Chroma. So this is a 20 to 80 beam splitter, non-polarizing. So let's go back. And then if I want to see what is the power meter in each and every detector, I would need to go to our analysis portal. Keep in mind that in order to do that, I would need to run the advanced analysis. So this is the spot coherence. So these are the two analyses that I've selected. We just move that a second, and then I would run the analysis. And then you would see the result. Let me pop it up, this one and that one. So now you can see that each and every detector, you can see the total power is 0.2, and this is the total power in 0.7. If I select the source and then go to its properties, then you can see the power meter is for 1 watt. Let's change this to 2. And then open the analysis portal again. We close these two, run it again, and then I would get an update on the power meter for those two elements. Now you can see it's 1.7. This is 0.4. So it was updated. We also added the option to put on screen those numbers. So when I select the detector, go to part info, then show incoherent power reading here. And then let's do it for this. Keep in mind that this number will be updated just when you run the advanced analysis. So if you do some changes and then you run propagate simulation, it will not reflect the right value. You need to run the analysis to get the right number of rays and to calculate the power. So this is, keep in mind that you are showing the right figure. The last thing that I wanted to show you is the coordinate system. So we now adjust the coordinate system to the size of the element. So I'm selecting now the detector. So it's nice to show this feature on detector. So you can see that When you have a small detector, the coordinate system is small, and you have a big one, it's big, and it's being dynamically adjusted to the size of the element. We have here another one here, which is very small. So if you can see here now, I would select the small detector, and you can see that it has a very small coordinate system over here. So this is, again, a nice feature. So I would segue back now to Roman.
Thank you, Gil. Thank you for staying with us. So we are back to polarization. Let me share my screen again. So polarization, again, a new feature released on the last release of August 1st, consists of actually two features. First one is the definition of polarization state of your light source. So far, all our light sources were unpolarized, and I'll show you in the moment how you polarize, how you define in different methods the polarization state of your light source. And actually now when you have your light source and the rays will interact according to polarization, so when the rays will be intersecting the glass surface, they will behave according to Fresnel coefficients. And if the surface have coating, it will behave according to P and S properties of the coating, which are provided by the manufacturers. Now, if you have this ability to polarize and to behave according to your polarization state, you would like also to see on your detector whether it's a incoherent spot or phase information. You would like to see the components, the XYZ components of the polarization. And this is the second feature. So let me just show you the example, and I hope it will be clear. So this is some simple two-dimensional periscope. So you see two mirrors which are tilted in different angles, in different planes actually. We can take a look what the mirrors are. So it's, you know how to go to optical settings. Let's go to the surfaces front, and you see the coating. You can see what to expect, and you see that at 550 is about 91% reflection. So it's protected aluminum. It's not perfect mirror. This is what we have in this example. And the second one is just the twin. It's the same one. Now let's start from the light source. We go to its settings, and then at the bottom of the setting, you see polarization, okay? So far it was unpolarized, now it is polarized, and there are few methods of definition. I use the simple one here, linear polarization, 0 degrees orientation angle, which says it is X polarized, or in this case, if you refer to the first mirror, it is P polarization state, and you can see the extinction ratio, whether in dB or here by the number. But what you can do, by the way, pay attention that if it changes to 90 degrees, it will be now as polarized or vertically polarized. You see the numbers here, Jones are changed. But you can go directly, let me just change it back, and you can define it here as a circular left or right, elliptical, or you can specify if you know your Jones vector or stock parameters. So you can fully specify your incoming polarization state for every source type we have. Now, let's do the analysis, and please note 3 detectors I put, the same detectors, but the first one is just after the light source, so we can see it is X polarized, horizontally polarized, and the second one is after the first reflection, and the last one is after the second reflection. So let's just go to the analysis portal, and you see is D1, is D2 with the nodes, and D3. What I do here, I mark every one of them. You see it's a new feature, it's in purple color. You go here to the advanced, and you see spot, coherent, irradiance, polarized. It is in purple. So you see here this purple color, and I mark compare, and I did it also for the second one, and I did it for the third one. And now I press compare selected. I will have 3 of them. So I just show you how it's easy to use. And then I open each one of them, and I can show all of them together. Now, please take a look. D1, you see everything. You see here is the new one. We didn't have it on previous analysis. So now it's polarization component. You can show all of them together, like in non-polarized state, but you can show the X, and you see everything is 1 watt. Everything is in X polarized because this is how we defined it. And Y is 0, and the Z is 0. Now, if we go to the second one, because you remember this scene, that it is 90 degrees rotated. So what you actually see now, just a second, what you see that X became Z. You see, and by the way, please, you see this 0.91 is the reflection, is actually the coating curve I showed you a few minutes ago. And if we go to the last one, it still will be in the Z rotation. Now, what is interesting here, we present here polarization component in global coordinate system, okay? So actually X on the first one becomes Z on the second and the third mirror detector, sorry. Now, in mid-September, we'll release here a toggle button. So you will be able to toggle between presenting the components in global coordinate system as it is now to all in local coordinate system. So here nothing is changed because it's metallic surface. So if you go to the local coordinate system, you will have all the way X-polarized state. So this is the first example. This is the second one. I would like to show you the Brewster angle. And you know that Brewster angle is the angle of incidence at which P polarization is depressed. Actually, it is 0. And S polarization is higher. And this is the method that you can maximize your transmission. So this is fused silica. You can see I used some window. Let us see its properties. Okay. So it's UV fused silica. And you can see also here in the material information, UV fused silica. Now, you see I put this window at 55.6 degrees angle of incidence. You can calculate, the refraction index of a UV fused silica at 550 nanometer wavelengths. You can calculate, you can use your net and find the information here. Or, for example, just a quick example, we can go here to the tools, to the material information, just change NBK7 as default, go to UV fused silica, here it is, and you see that at this angle at 56 vicinity, you see RP is 0 and RS is about 12%. So you see the angle. Okay, you of course can download this and see in better resolution the exact angle. But you see it's pretty, it's not very sharp. For a region of few degrees, the P is 0. So again, I put 2 detectors. One is the reflected, and by the way, nice feature. I show here, if you go to view and to palette, and I show it's can be an intensity-based color. So you see actually that most of it is going through and much less is reflected, but let us see what is much less. So let's go here, and this is D1, okay? So you see the polarization state that, by the way, I didn't tell you, but also this one was, you see linear polarized, and you see it's 0 degrees. So it's horizontally polarized or P-polarized. So what you expect here, that P-polarization will not be reflected and everything will go through. So you see everything here in the incoming, in the transmitted one is X-polarized, and you see Y is 0 and Z is 0. And if we go to the reflected one, D2, it is totally 0. Also, you can just click on none, which is sum of everything is 0. You see X0, Y0, and Z0. Nothing is going here. So this is the second example, and the last one is a co-feature. That's actually what you can do now because we have a polarization, and also we added a new feature that you can add actual coatings to every surface of elements from our library or to the step files that you upload. And what you do, you see it's simple window, you go to its properties, and front, by the way, it's nothing. You can have it coated, and you can select from what we propose. We propose total absorber, ideal reflector, few types of beam splitters, 50-50, 70-30, 30-70, and ideal broadband anti-reflection coating. This is some predefined coating we add, but what you can do, you can actually you can create your own one. So you download the template, and you see here, it is the template is the simple one. You see the wavelengths, and you see the transmission and reflection coefficients in P polarization state and the S polarization state. And what I did for this example, I just created a simple one from 550 to 556 nanometers. Everything is P polarized transmitted, and the rest is zero. So I applied this coating, did import, and you can see when you do it, you can press coating chart. Let me do it again. Ground surface. Here. So the previous one was uncoated. So you can see, if you point here on the curve, on the green one, you see transmission is 99% P, and the rest is zero here. Okay, now let us run it. In this case, the light source, I put it to be Y, or vertically polarized. Okay, you see 90 degrees here. So of course, what I expect, if this want to transmit P and I hit it with S, it will be actually a blocker. Let us see it. So in the analysis, let's go to G1, which is input, just after the light source. And let us see, you see it's nothing in X, everything in Y, okay? So it's vertically polarized. Now, if we go to the second detector, and pay attention that when I select a detector here on the analysis for tau, you see the detector on the layout is highlighted, so you know where you're looking. So here you can see zero in X, in Y, and in Z. Everything is zero. So actually, you see total power is zero. So what we created here, we blocked. And of course, I can create it, I can rotate it now by 90 degrees, and it will be now in the P-polarization state, and this window or this polarizer will transmit everything. So this was just a nice example of how can you use our coatings with our new polarization features, the setting of the light source polarization and analysis in polarization state, and dividing it into polarization components. Thank you for listening, and Gil, back to you.
Okay, Roman, thank you very much. I would like to finalize this and to, again, thank you for everyone that has participated. I've now shared a discounted coupon on the webinar chat. It is available for a week up until the end of the month, 31st of August. If you want to, some people are purchasing via a purchase order, so just send us an email to info@3DOptix.com and request that discount, and you will be able to get that. You will get an email very soon after the webinar with more details about how to get those 50% discount. If you have any questions about the new feature or any question in general, don't hesitate. Typically come back to you within very quickly, within a few hours, and you'll get an answer. And I hope you'll try out those new amazing features. I can see that some of our premium users are already using them. So we are very happy. So thank you very much, and I'll see you on our next event next month. Bye-bye.